Um, awesome. And then I made it so you could share your screen. But Glenn, will you tell us a little bit about yourself, who you are?
Hi, team. Hey, it's good to see you. So I work at Johnson Space Center over in Houston. My job is to work with other engineers and the mentors and astronauts to come up with the projects that you guys are working on. And so I'm really excited to see what you guys have to show us today.
So
Glad to be able to
how did
just
you come up with this project? Who asked for this project, the trash ejector?
Oh, actually, so um, when I went to Russia for some training, I saw that on the Mir space station they had a trash ejector. And when I started talking around NASA, we said, we're probably going to need something like that when we go to Mars. And so this was a coordination with some of the other engineers here at Johnson Space Center. But it came from ideas that we've kind of gotten from Russia. But of course, we also had a trash ejector that was used on Skylab, and that was the very first space station that the U.S. flew back in the early 70s.
Awesome.
So,
Okay.
okay.
So, team, introduce yourselves and then you can share your screen if you have a PowerPoint, and then we'll see your prototype.
sounds great with us.
Okay.
My name is Jaden Sakraj,
I'm Aiden Hector.
I'm Nathan Kepler.
and today we are going to show you our prototype, also known as the flying torpedo.
Oh no. Sounds dangerous.
How bad it sounds.
All right, I'm going to share your screen for you guys. All right. All right. Confirm that you can see our screen.
Yep.
Excellent. And okay.
All right, so Aiden, take it away.
Let it load. There you go.
It's
So
there.
the problem we're addressing is that astronauts waste too much power and fuel releasing trash into space. So we're trying to figure out a reliable method to launch trash out into space without consuming too much power. So our inspiration is taken from tennis ball launchers and torpedoes, the way they launch out using wheels just to send it out and fly it out.
Our first sketches were based on springs and airlock mechanisms. And it was obviously based on the tubes of a torpedo. But we were quick to know that we couldn't use airlocks while in the spacecraft. So we had to brainstorm other ways of launching the can. So this was the sketch that mostly resembles our prototype right now. As you see, we have the wheels right here. We have a power source, and we have a door mechanism that we haven't come up with yet, but we're currently working out ways to figure it out. We also have a loading mechanism, which we currently are working on right now, and it's currently printing. So, you already know the criteria, but just to sum it up, we have to launch the Sukan off the edge of the table, and we can't exceed a certain speed.
All right, so the part you've all been waiting for, the pros and cons of our prototype. So the best parts of it is that we can launch it at a fairly regulated speed. It doesn't really exceed 1 meter per second. And we're only using one motor for this, meaning that power consumption will not be that high when we're using it. However, in the current state of our prototype, loading is not our best aspect. However, as Nathan said earlier, a 3D part is currently being printed for our prototype, which will allow the loading mechanism to be more consistent. Speaking of our 3D part, let me present it to you all in a CAD state. So this is meant to be a container that which we can load the cannon from the top, we can activate our prototype, and it will launch from the side, as you can see here. The divots on the wheel on the side are meant to be holes so that the wheels, which you will see in a second, will end up launching. So without further ado, I present our current prototype, which implements the inspirations of our torpedo tube and our tennis ball launchers into a method where we can launch our empty soup can off a table. And without further ado, here it is. Just
switch it off here and live camera now.
that would be great, thank you.
Yeah, stop sharing.
Okay.
And Nancy just joined us. Hi, Nancy.
Hi.
Hey,
So they're going to demonstrate their trash
You
ejector.
got here just in time to see the demonstration. This is
okay, yeah, I had a phone call and I couldn't get out of it and just
Not a
sit here,
problem.
so- okay, good. Okay, let me pin them so
Okay.
I can see it.
Oh, yeah, that's a good idea.
All right.
Okay, show me what you think. How does this get loaded, gentlemen?
So this will be loaded from the top up here down into here.
Yep. Very good.
And then we have a button at the back here. This button, when we press it, it will activate these wheels and cause everything to start running.
Oh, okay. So did I see that the pusher plate is rotating? Is that correct?
Mhm.
Yes,
The orange.
this is rotating.
Yeah, very good. So when that rotates, look at that. So you guys are using one motor to spin the can as well as to spin the wheels. Is that correct?
Yeah.
Okay.
Very smart. Okay. Keep going. Let me see it. Can you throw it right now or not?
Yes, we can.
Oh, excellent.
Oh, I see it. Yeah.
Very good.
It would be preloaded.
But
Yeah.
we have 3 part being printed for that, which is not finished at the time of this presentation.
Yeah, you need to. Okay.
No, that's fun. Okay. And yeah.
Nice.
Okay. Now, so one question for you. The spinning of the pusher plate, does that give you any real rotational motion as it exits?
Well, as of right now, because we don't have the holder to hold the can, it
Mhm.
can't really serve a purpose right now. But
Okay.
once that's printed, it should allow the can to spin and launch out at the same time.
Okay. And I'm curious how that's going to work. Now you know that it's not required for it to have for it to spin it but I like that you're working on it. Just as a thought, do you think there's any chance that you could get any of that spin from the wheels themselves?
I feel like that is possible. And it will definitely be hard for us.
How do you think you would do it?
I feel like the only way we would do that is we put the wheels on an angle.
And that's what I was thinking too. And I see why it would be difficult for yours because you're trying to get all of the motion from that one motor. But I like how you're doing this. I don't have any suggestions, but I think that you guys are on a really good path. This looks great, team. Okay. So you're going to insert that 3D printed piece and then kind of reassemble around it. And then are you going to have some kind of a container on the outside of that for pressure, keeping from losing air?
Our major focus at the moment isn't really the hat, more so getting our can to launch. So we haven't really considered like airlocks, hatches, that sort of stuff. Our main priority right as of our current moment is just getting the can to launch.
And I think that that's great. Okay, that sounds terrific. I'm going to let Nancy ask some questions here.
Okay. No, look, yeah, it looks real neat and stuff. I guess the one question I have is since it's launching and it's, it's following that curvature. Do you guys have a way of measuring the distance that it travels?
You may be thinking to measure the distance it travels, we may just use a video
Yep.
and measure
Okay.
it.
Yeah, because one of the things I noticed Glenn says is he doesn't want it to go more than 1 meters per second. So yeah, if you have a video, and I told the other team you could just put a tape underground, see where it falls. You can calculate how long it travels, the distance, and then just using simple math, you can get the velocity it travels and stuff. So and I definitely recommend you take video of it. So you can also have that, and you can see how far it goes. But yeah, this is real nice. I like how you guys put this together.
Thank you so much.
Thank you.
Yeah, it's a really good design and it works really
Yes.
well. Now, the one of the requirements was that the can has to be full, and your cans are empty, which I enjoy because it's safer, right? What do you think is going to happen when the can is full of?
Well, going off to be obvious, obviously it's going to have a little bit less distance due to the sheer weight of our can.
Yeah.
However, we should still be able to load it and launch it despite the shortening of the distance.
Mm-hmm. Yeah. So that's where the 1 meter per second comes in, with a loaded can, not with a empty can. So that's a little bit different. So think about that also.
That's right. Okay. And I think that the stuff that the equipment that you're using there, is that all Vex parts? Is that right?
Yes.
Mm-hmm.
Excellent. I think I'm really glad that you're prototyping with some of that stuff first, and that'll help you move your project up a lot. Have you been thinking about the exterior hatch?
We were thinking of like having some sort of tube where we can insert the can through the side and then it would just move down into here.
He's talking about the
Okay. Well, I don't think the interior hatch is as difficult as the exterior hatch, right? Because you have to be able to open the exterior hatch from inside. Have you thought about how you wanted to do that?
As for the exterior hatch, not precisely, as I've stated before about the whole focus thing and how we're just trying to get our can to launch. So we haven't put much thought into the exterior hatch as at the moment.
Okay. Another question for you. When the can is in there, how much are the wheels squeezing the can?
We made it so that it doesn't squeeze too much so that it can't exit, but we also made it so that it can go a little bit outside and adapt. It can go a little bit outside and adapt as needed.
Give it a 90-degree turn.
Okay.
So,
Oh,
so we made it so that it
there
goes in and out.
yeah, let me see it that way. Oh, very smart. I like how you've done that. Okay. And part of what I was thinking about was that right now you're dealing with an empty can. And so I thought maybe it could be pinching the can, and that wouldn't be possible when it was full. But I think that you guys have it arranged in a way that's really smart. Okay. I look forward to seeing how you do that exterior hatch. The fact that you guys already have some experience with gears and things like that, I think that's going to help you with deciding how you want that door to open, right? Because from inside, you can imagine well, there's 3 different types of door, right? Here it is. So imagine I can have a door that opens like this.
Mm-hmm.
I can have a door that opens like this, and I can have a door that opens this way, right? And so using some kind of a gearing for each of those is not that complicated, especially if you've already got a handful of gears to kind of play with, right? So consider if you've got it like this, you're looking at a hinge. The pin for your hinge can become an axle for rotation. Does that make sense? So I think you guys have a lot of options with how you're doing this. Excellent job, team.
Thank you so
Do
much.
you have any questions for us?
Um, no.
Not precisely.
Okay. What do you think your next step is?
I think our next step is to attach the loading mechanism and test it to make sure it's fully functional, doesn't cause any problems. And then next, we may just solve the opening the door mechanism, how to open the exterior door.
I think that's a great process. Good job, team. Keep this up.
Thanks,
Thank
fellas.
you so much.
Thank you.
If you need next class, just sign them, and I'll actually the bell's going to ring to release third period now anyway, so don't worry about passes.
Right.
All right, thank you.
Thank you.
very much.
Thank you so much. Have a great weekend.
You guys put it back in your project box. Okay. Just be mindful that you got a dangling battery there.
Awesome.
All right, hello there, Glenn.
Hey, how are you doing? Good to see you.
I'm doing well. Good to see you. So I've got a little transition now. I've got a team coming in right behind this one. So what I might just do is kill audio and video, get them set up, and I'll be back with you all in about 2 minutes.
Okay. Thank you, Chris. So, Glenn, I have a question for you. For this trash ejector, do you want it to be able to angle like right now, their trash is going out, exactly horizontal on a linear plane. Do you want it to be able to angle down or up, or it doesn't
No.
need to? Okay.
No. And so I want it to come out at a speed less than 1 meter per second, right? And I gave them the option of can they get it to twist, and that the idea is just to be able to make it, so it's a little bit more straight coming out. But that one is not a requirement. It's just a nice to have.
Okay.
Oh,
Okay.
you were breaking up, but it sounded like you were in between classes.
Yeah, I think you could just close that door, guys, so we don't have to hear passing. Yeah, they're here, the next group. And it's interesting, you're going to see the empty can demos, because we were starting to get little dribbles of chicken noodle soup all over the room with the full cans. So we decided to go empty just for initial.
Yeah, that's good.
Completely.
All right, boys. We need 4 seats. Yeah. All right. So you might want to just do like an arc and have one person control the clicker. All right. This way you all can be seen and heard. Just make sure you project nice and loudly if you're a little bit further away from the laptop. So
actually, just a reminder today, Philippines blood drive located in the East Gym. Please consider donating. And remember the bar.
I'm Zach.
let's let the squawk box.
My name's Arjun.
Let's let the squawk box.
I'm Ryan.
All right, start over. Hi.
I'm Zach.
Hey, Flo, are you recording?
Yes, I am.
Flo, are you recording?
Oh,
okay.
Yes.
All right,
yes.
go ahead.
Okay, go for it, guys.
I'm Zach. My name's Arjun.
I'm Ryan.
Awesome. And Glenn, you want to briefly introduce yourself, because did you hear Glenn introduce himself before?
did not.
No. And Nancy.
All right. So I'm Nancy Hall. I'm the NASA Glenn Research Center regional mentor for schools in my area. I'm over at the Cleveland, Ohio, and I mentor schools in Wisconsin, Minnesota, Missouri, Michigan, Ohio, and parts of New York. Looking forward to hearing your talk. Glenn?
Hi, I'm Glenn Johnson. I'm at Johnson Space Center in Houston. And I work with engineers and astronauts and the mentors to come up with the projects that you guys are working on. So I'm really excited to see what you guys are doing.
We'll start first with our slide deck.
All right, let me get you going there.
We see the deck.
Take it away, boys.
This is our HUNCH Trash Ejector PDR.
You already did your intros. I'll move on.
Yeah.
Right.
So the problem is, what is the most effective way to remove trash from a spacecraft on its way to Mars without losing air? So as humans travel space, they need to find more efficient ways to use fuel, and so that's the problem we're trying to solve.
Left click. There.
So we researched a little bit about football launchers and baseball launchers to for inspiration on our shoot fuel mechanism, and when the wheels are like rotate in opposite directions to shoot our can.
And here's some primitive sketches we drew at the beginning of our project to brainstorm. We originally imagined a tube with a piston that would push the can into angled wheels for a spiral, and we wanted it to be fully automated, where it would just be a button press that activates everything in order. And we also had some other ideas, which we did not draw, which was a spring-loaded mechanism that would store potential energy and release it, and a piston-powered mechanism, which would be like really fast. And here's an additional sketch we drew showing like how an astronaut would put the can into the tube and close the door. On the back of the door, we imagined a piston attached to a plate that would push the can into the tube, into the wheels. Sorry, but a problem with this was that we imagined was where we'd put the mechanism for the piston, because you don't want a lot of weight on the actual door itself that make it unstable.
Feel free also to use the cursor to point out parts in the picture if you want.
So some of the criterion constraints, the mechanism must not launch off faster than 1 meter per second to prevent denting. And the mechanism should be a simple design. The mechanism must have some kind of handle/release for the astronauts to be able to release the trash effectively. And the mechanism must be energy efficient, as energy is finite and valuable in space. Some of the constraints is that the mechanism should not be complex and should not use too much material, as we were trying to make this as cheap as possible. And the mechanism cannot be heavy, because the heavier the mechanism, the more expensive it is to launch it to space. So some of the designs and solutions that we were thinking about was a spring-loaded mechanism due to the powerful launch. However, at the end, we determined that this would be too fragile for us to use in our final project. We also looked at the wheel-powered mechanism, and we determined that this would have a fast launch, which was better for our goals. However, this would be more complex, but with the way we built it as simple as possible. So our overall choice is to use the wheel-powered launch.
This is our current prototype. It's a 2-wheel mechanism. Each wheel is controlled by its own motor. The motor is connected to the wheel using a gearbox that has a 3-to-1 gear ratio in order to make the wheels spin a lot faster than the motor's actually spinning. The tube was originally designed to fit the can with less than 10% volume, so we didn't have to use a vacuum tube, but we ended up, as we built it, we realized we wanted to extend the tube because for how we pushed the can into the wheels. And then this is the designs that we're working, our newer designs that we're working on implementing in the future. We will extend the tube, and we will also have this L bracket that's connected to a drive shaft that'll be connected to a servo module. Servo module will spin the drive shaft, and so the L bracket will evolve and push the can into the wheels, shoot out. And we're also working on developing some sort of a door, although we don't have much progress on that as of the moment. And
is that the end of your
that's
deck?
the slide deck.
All right, you want to go live and
yeah.
First show them the features, and then you'll go ahead and do a demo, okay?
So
speak nice and loud.
So these are our motors. We're using two Vexbolt motors. This is our 3-to-1 gearbox ratio, which is connected to our flywheel. And the can would just be placed right in the tube, and the tube makes sure that the can is launched straight and direct
And our battery is over here, and our brain is right.
And we also have something that you didn't see on the slide deck. We also added a button to turn the wheels on and off. And I will show you how it works.
Whoa.
Okay,
That is
that
the
looks great. Okay. Now, I see that you've got two motors. I'm guessing that you had to gear them down a little bit so that they weren't spinning too fast. Is that right?
Yeah.
Okay. What happens if one of the motors doesn't go? Will it, or it isn't powered? Does it still go out pretty much the same or not?
Well, both of the wheels are spinning, and if one wheel stops spinning, the other wheel will spin in the same direction to launch the can out. So although it might launch with less power, it still will launch out. The plug one. So we're gonna unplug one and see how it works because we've actually never tried.
It just won't go as on pressure.
Oh,
It actually gets stuck.
Does it jam?
Yeah, gets jammed.
Okay. Now, that's not all bad. It's something to think about, right? And the other thing I was kind of curious about is by having two motors, it's possible that I could have one spinning a little bit faster than the other one. And so that's just something to think about. Decide, you might do a little bit of experimentation to find out how that might play out. Because it's hard to have two motors that are spinning at exactly the same rate. There's all kinds of little factors that could cause it to be a little bit different. Now, I also saw that you were planning for it to be a little bit longer of a tube. Is that can you explain a little bit more about how you were planning for that to happen?
So we're gonna in CAD print the design. We're gonna extend this, but not include the holes for the wheels, obviously. And then we will include a smaller hole where the L bracket will go that pushes the can into the wheels. And
Okay.
it'll be basically we'll use some sort of adhesive to glue it to or attach it to here.
That's okay. And
Yeah.
so I'm not sure, I don't think I quite understand. So you insert it, how is it going to move forward to get into the wheels?
That's
we go back.
You mentioned an L bracket, but I didn't see how that L bracket was getting its motion.
Yeah,
to
that's what
move.
I was wondering too. Is that L bracket designed to move it?
it's so it'll be connected to a servo module connected to the brain. So when you press the button, the servo module will spin, which spins the drive shaft right here, and then the bracket that is attached to the drive shaft will revolve around. It'll revolve around the drive shaft, and it goes into the tube and pushes the can.
Okay, so is the plan to simulate like you have an airlock, you put the can in, you close it, and then this pushes it forward till it hits the wheels and then goes flying out?
Yes.
Okay.
Okay. Do you need a servo for that, or is that something could you do that same motion with just a lever?
Yes, we could.
Yeah.
Backup.
Yeah, because that's just a lot of electronics. Yeah, I think that's what Glenn's thinking. Yeah, if you can do it something simpler, yeah, you want to try that.
Yeah, we'll look into that.
I'm not opposed to what you're doing. It's just that, if you can make it simpler, that sometimes that's helpful. Okay. I like your style with this. I think this is a great idea. Have you been thinking about your hatches, your hatch inside and your hatch outside yet?
So
We haven't got so much into that, but we will work on that in the coming weeks.
Okay. I mean, so for example, sorry. So I just got one a big pipe here. So imagine you could have, there's at least 3 different doors that you could have for this, right? You can have one that opens like a regular door at your house. You could have one that rotates up, right? And you could have one that slides open, right? And um, part of what I'm thinking about is that um, when I was a kid, we didn't have any automatic windows on our cars, right? You had hand cranks and you would crank it up and crank it down.
Yep.
Remember, you don't have to have electrical for everything. Some things you can have that same way, right? And my reason for bringing this up is um, you may not have a whole bunch of motors to throw at this, but you can have a couple of hand cranks and you can have some gears and things like that. And that'll keep it pretty simple. Okay. Excellent. Do you have any questions for us?
I have one question. Do you think it would be better if we reduce the 2 motors that we have to launch the can into like 1 motor somewhere?
Um, Maybe it's not a requirement, right? The idea of having 2 motors, um, it, by having 2 motors, it could be a good backup system, right? The question might be, if one motor isn't working, will it allow will it stop that wheel from turning, or will it free spin? Does that make sense? And so if you've got free spin, it may go ahead and launch it anyways. It might be a diminished rate, but it would still launch. So that's something to think about. Okay.
Mhm.
All right, thank you, boys. Why don't you go ahead and pass this to go to the next period? All right, very nice job.
Yeah.
And team, we've got one more presentation, and we're going to transition from shooting trash to Nanolab.
All right. Thank you very much. Have a great
Terrific.
weekend.
Thank you.
Excellent job, team. Good job. I
Nice
really like it.
demonstration.
Thank you.
You guys can take the can too. I'm just going to slide in and get stuff set up for you, girls, before we get going.
I appreciate you keeping us on schedule there. That's awesome.
It's more about just making sure I get the kids over to where they got to go, you know?
Yeah, that's good.
Let's see here. We'll get elevators.
It looks like you've got a lot growing in your class there. That's amazing.
Isn't that something?
There's a lot going on in this room for sure. We actually just had our first harvest, which we donate last week, and I think we pulled 100 pounds of leafy greens out of the room, and we're going to do that again in 2 weeks. So every 3 weeks,
awesome.
Now. All right, I'm going to turn you over here to these engineers, and we'll give them a chance to give you a little presentation. All right, come on in, ladies. Fellas, you need to
Good morning.
Morning.
Hey, ladies, how are you doing?
Okay. We did. We're like getting to the slideshow now. Do we just put it here?
No, so we're going to have to share your screen. I'll make that transition for you. Why don't you just go ahead, tell them who you are, let them tell you who they are, and then we'll do your presentation.
So hi, my name's Navia. I'm a senior in high school. And I'm Katie.
Excellent.
Awesome.
I'm Glenn Johnson. I'm at Johnson Space Center in Houston, and I help come up. I work with a lot of other people to develop the projects that you guys are working on.
Yep. And I'm Nancy Hall. I'm the regional mentor at the NASA Glenn Research Center in Cleveland, Ohio. And I actually came up with the Nanolab project with help from Glenn. So looking forward to seeing what you guys have come up with.
Awesome. So we're going to go ahead and share your screen and get your presentation pulled up. All right. Confirm that could be seen?
Yes, we can see it perfectly.
All right. Off you go.
Looks awesome.
So today we're going to be presenting for you our Nanolab design for the HUNCH project. Just to start off with a little project overview, in a zero gravity environment, because astronauts need a reliable food supply in space while also accounting for the water flow challenges, we decided to solve this problem by coming up with an adaptive nanolab design to be able to enable efficient spacecraft production. And our prototype is designed to deliver an operational mechanism to keep the growing media continuously flourishing as well as controlling the water. For the prototype, we were trying to build it to introduce water into the growth media with the nanolab setting because it poses a few unique challenges where we can't allow the water to just go on a different constraint outwards, which is why we're trying to contain it within our environment. And because of that, our objective was to design and build the nanolab where we could optimize the growth conditions for experiments in the microgravity environments while ensuring effective nutrient delivery and hydration for the plants. For our solution, we designed our prototype to focus on facilitating water introduction into the growth media within the nanolab environment for the zero gravity applications. And our mechanism allows astronauts to be able to access fresh, nutritious food while allowing longer stays in space and supporting the survival in more distant locations. Our prototype meets their needs by improving efficiency and delivering water directly to the soil where it's required and monitoring the soil health to ensure successful crop growth.
So our criteria was to design, build, and test a fully functional 2U size nanolab for material testing system. And this would be able to allow NASA researchers to explore the fluid physics of different potential growth media materials. And we had to include the option to change the growth media materials, a method for moving fluid in and out, required sensors, electronics, and the overall system can be studied and self-contained. So we did a lot of research. We found several existing current commercial systems that address similar needs, including the passive orbital nutrient delivery system, the advanced plant habitat, veggie and plant water management soil. And these systems are currently used to deliver water and nutrients effectively to growing media without conflicting with the challenges of a zero gravity environment. So to have those sources to like get inspiration from, that was a really good source.
This is the left.
And then because our criteria prohibited any electrical or mechanical mechanisms, we had to ensure throughout our design process, the system required minimal manual labor while still allowing astronauts to effectively grow crops in space. And we did use sensors though, which
because they come as underneath the criteria for the mechanism that we had to create, it still went along with the criteria. So we didn't have a problem with implementing it into our solution with it going against the electrical or mechanical mechanism prohibition.
Okay, so quick question. I want to jump in. Where does it say, because I didn't think it prohibited, when you say prohibited electrical mechanical systems, I'm just wondering what you're referring to.
So on the HUNCH website, they have the PowerPoint presentation for the Nanolab, and on it, they encouraged away using electrical and mechanical engineering. So we implemented our solution to be able to use as little to almost nothing for it, other than our sensors, which come down as a requirement.
Okay, all right, yeah, because I think it may have been minimized. I don't think it wants you limited, because you're right, the sensors are in fact mechanical and electrical systems. So if you minimize it, let me see what you've done. Yeah, I don't want you to eliminate it. I may look and see what it says, but that's a good question. Go ahead.
So for our design, when we originally went into looking at it, this was our original design that we started off with. And as you can see, we originally implemented our box to be horizontally implemented, and underneath it we'd have a water reservoir with tubes instead, but still using capillary action to get our water introduced to the growth media. But our constraints were that we wanted to implement a misting system, but the misting system would require electrical engineering and mechanical engineering, which would take away from the system. But also, if we had to implement it with the water reservoir box, it would be using it for the same purposes, and we wanted to completely eliminate the redundancy.
Mm-hmm.
And in our second mechanism, we wanted to implement a syringe instead, where we'd implement a little spring to be able to push the syringe so that the water would be effectively introduced to the growing media at a slower rate for as long as it would need to in the experiment trial up in space. But then our only constraint was that if we had to put a spring in, then there wouldn't be a initial push to be able to allow that spring to expand, pushing down this area of the syringe to be able to give the growing media the water that it needs. So we removed that mechanism and moved on to this mechanism, which goes back to our original design, where we still implement our capillary action with our growing media box instead. And we have the wicks from the wicking system implemented instead at the bottom of our box into the growing media box itself to cause a puncture reaction. And then it would start up the capillary reaction just from that one mechanism.
Oh,
yes. So we actually have our
reconnect with you.
Yes. So we actually have our box right here. So the entire solution would be that we have our little latch here that would get a key to be able to move downwards, but then the growth media box itself would be able to go down and puncture into our water reservoir here from one initial push, where we'd have ridges on these rails on the side with springs that expand the second that we remove when we push in the latch, causing it to go down.
So your idea with this is that before the drop, it's in this position, and just as you're about to drop, it comes in and it punctures. Is that correct?
Yes.
Okay.
Very smart. I like what you're doing.
It's unique.
Okay, and then I want to let you know I did go back and look, and there seems to be a little bit miscommunication. So it does say no mechanical electrical, but it also says due to limited resources in space travel, the ideal water delivery system would be passive. That's not saying this has to be passive. So we're not telling you not to use that, because in it, it specifically says we want you to have sensors. We want you to be able to look and see what's happening with the plant's growth. You should have like a camera or some system in there. So this design is good, but if you find out you need to use mechanical electrical systems, because you're going to need some sort of camera to view this. You're going to need something mechanical in there. So you can use mechanical or electrical systems. All that we're saying is for an ideal system, you want it to be passive, and mainly because electrical mechanical system breaks over time. So if it's something that passive, and this is an ideal situation. So as you continue to design, if you find other things, so that pushing mechanism, if you want to use something mechanical, you can do that too. And the other thing I noticed is in your summary, in your constraints, you listed two different length, 10 by 10 by 10 or 20 by 10 by 10. It's the 20 by 10 by 10 that we're using, and I'm glad to see this is vertical, because that's the one that's being used. Again, it was just describing different sizes. So, but yeah, I like that idea. The only thing you want to be aware of is when you push that button to bring it down, it may be, because it may be a couple of hours before we actually drop it. So you want to look and see what all's happening in there. And like I said, something else you want to have a sensor that measures either the pH, the water, or something, and you also want to have a camera that images it. So like I said, you can use electrical system. Okay, so you want to look at that, all right?
Wait, Nancy, right now, I think yesterday you said that part of the when we hook up with the USB cable, that cable sends the signal saying we're going to drop.
Yes, so they can have,
And so, so that signal is what could send it into the water, correct?
Yes.
Okay.
So that's what I'm saying is, so if you can set that switch rather than making it manual, set it with, you could use the electrical so that it gets a signal from the USB. And there's Arduinos or Raspberry Pis or something you can attach to that. And then once it gets a signal, that'll push it down. Yep.
We also just wanted to point out in our CAD design here, on the sides of our growth medium box, we did leave some room for when implement the sensor, so that's why there's like a little bit of the extra space on this side.
Okay. All right. Yeah. No, I'm glad you thought of that. Yeah. And that, like I said, that was an ideal case. So yeah, no, that'll be perfect. Yep.
Okay.
And then just remember the USB connection is on top. So the fact that you have your water and everything in the bottom is a good design.
Thank you.
And Glenn, I see you're thinking about something.
Well, I was going to ask, oh, I see. And with your picture there, it makes sense. So you've got a camera up top so that you'll be able to see how water is moving into the soil or your medium material. I think that's really smart. How much water are you thinking to use for this?
In the actual presentation, they told us that they would already have a amount that they would have us put into our box, which is why we made it specifically to only take up a certain portion of the box, since the growing media box still needs space to fit in on the top, as well as fit for the space for the actual growing media to go upwards. But for right now, we didn't really focus on it as much when we had design specifically, but in our physical design, we have it implemented.
Okay. And part of what I was thinking is that, it's a 5-second drop. And so having a lot of water is probably a bad idea.
Yeah, you don't want a lot of water. Yeah.
You're probably talking somewhere around 20 milliliters.
Yeah.
Is that a good guess, Nancy?
Yeah, because the thing is, you're not going to see it grow. Mainly what we're looking at is we do want to see it puncture and as the water starts moving up. So this is one of those where you want to set it right as it's about to drop, because you'll be able to see it puncture and see the water move up from the capillary. You will not see the plants grow, but you do want to test it in the lab and get an idea. And this is something good for you to do. How long does it actually take for the water to grow and everything too?
Right.
The water to grow, for the plants to grow.
Well, do you need plants in there?
We want them to have something. If we want them to have some sort of substrate, some sort of material. For their material, they want to water its plants. So if they want to put the plants in there, I don't have an issue. I'm just talking from a research standpoint. You may want to see how long it takes it to grow, because that's good information just to have and to say, hey, over time, this is how long it'll take. And you can even track how much water does the plant need over that time.
We actually did test out a trial with an alpha plant that we can show you.
That's gonna be later.
Yes.
Okay. Look at that.
Yes, just so go back.
Yeah, once we get there. Okay, so that's just in a little bit, but again, just going back to our original prototype, again, we originally thought horizontally oriented, but that also came with a lot of different flaws. And then so we pivoted, and actually on the right here, this is our original, like from this sketch, this is how we sort of thought we would have like a syringe being pushed by like a spring, which we tested building out on CAD, and then we would have our little growing medium box, and then soon after we did pivot to our vertically oriented design. Okay, so next.
So then, do you want to go talk about
so the prototype models, if you see in the picture the red box here, this is our growth medium box. We originally did put in a little divider, so maybe we could test out have two different types of grow medium at once. This is just the sketch again, and then this is the the CAD file which you guys saw already.
This is also the wicking material, if you can see right here, that we have implemented at the bottom of our growth media box to be able to cause the puncture into the water reservoir box.
So you can show them that when you go live.
Okay. And then this was our 3D CAD design, as you saw before, where we have our water reservoir here. Above the water reservoir on top of the box, we have a thin film that we're creating currently to be able to cause that puncture, where the wicking material would be able to go down and puncture into this material. That would give it access to the water, introducing it into the growth media through that capillary action. And this is also where the wicking material, which is the thin kind of cotton material that would go on here, is what punctures in and kind of stimulates that capillary action.
So we did do, as we stated before, the growth medium test. We used the MV1 units, and we tested out 4 different types of growing medium. We used sponge,
One type of soil that we ended up
Yeah.
using was the alkalite. It was arsalite, and then the other one was the perlite vermiculite blend, which was over here.
Yes.
One of them was we used the arclite because it was arsalite because it was that one was the lightweight.
It was a very
That one was a very absorbent, and then our perlite vermiculite blend was the one that we chose to be a lightweight version, and then
so we grew alfalfa.
yes.
Go back.
This is the growing media that we tested, which is what Katie was talking about.
We tested out these 4 different types of growing medium, and we grew alfalfa for its quick results. And we do plan on like conducting more in the MV1 to test out more different types of plants and continuing with our research on that too.
That's very nice.
And then just for our next steps, the few implementations that we are trying to push into right now and focus on before going to CDR is the implementation of our twist latch, which as you can see for here is this implementation where we have to work on causing it to be able to see if we can find or create a key to be able to do it so that it mechanically can be pushed downwards. And then as well as from that, we're also working on implementing the thermometer, the humidity sensor, and our camera in the space that we were showing you before. And we also, one of our peers has been working on a crane for the SMG for conducting the additional tests in the MV1s to be able to put a petri dish with our growing media inside to be able to see how it responds to this zero gravity environment.
That's a neat device to use. Yeah, that's very cool.
Thank you.
Stop your share.
Wow.
Yeah. No, that's very good. Yeah, like I said, you had me a little concerned at the beginning when you said no electrical, mechanical, because I'm like, where did I write that? But I'm glad you guys are looking at sensors and all that. So yeah, that looks real nice.
And then
go ahead. Show us what you got.
Nice.
This is the actual box. This is the Nanolab environment that we created, and this is the space, as you can see, it's just behind the tape. This would be the space where we implement our motion sensors.
Humidity sensor.
Moisture.
Oh, nice.
Moisture.
Moisture.
And then.
So is that a capacitive moisture sensor? Is that right?
Yes.
Okay. Very good. Keep going.
The Raspberry Pi that we have implemented in our box in the space that we could implement it in against either our growing media box or near it. And then this is on its own, where this part would be upside down in our growing media box, already implemented there with this material.
Excellent.
Okay. And what is the red part of the box? What type of material is that?
This is the acrylic material.
Okay.
This is the acrylic material, and this is the 3D print material that we used.
Yeah.
But
we
then
plan on redoing or like reprinting this because as you can see now, we originally were going to use the sponge, but after our test, we found that the
soil works.
Yeah, the
soil, okay. Yeah, the reason I say that is with the electronics, putting them at the side is good, but make sure it's not going to be in contact with this and the water. So that's the one thing you want to make sure. Okay.
This box itself would be clear for the view from the camera to be able to see.
Nice. Okay.
And
so
this is the material.
Where's your camera going to be placed?
We were hoping to be able to place it in the top of our box.
Yeah,
we be able to.
We definitely this.
And so
a little smaller, and then obviously reprint this to like as we tested.
Okay.
Okay. So if your camera is up top, where do you want to place your light?
Our light would also be implemented at somewhere at the top. We were hoping that would be able to, once we reprint it out, to be a little more constrained so we have extra space at the top. We could implement it at the top to be able to go and view down, like looking down at the growing media.
Okay. Just a thought. You might have one light up top and then have because you're going to have a transparent box, you might put another one down low or a couple of them down low, and that way you get transmission light as well as the reflective. Does that make sense?
Yeah, and I was going to say with the light, you can also get a little strip to light it because this is going to be enclosed, covered, and you want to test it enclosed and see how well the light works. And then with the making it clear is actually a good idea. That way you can see it.
Now, another thought, you might add food coloring to your water. and that by having a darker water come in, you might be able to see more of it as it gets absorbed into your soil, and choosing the right color might be valuable, right? Anyways, though I like what you're doing. The thing that impresses me the most is that you want to set it up. So you want to set it up in the drop tower, but you don't want water to make contact until you're getting to that 0G position. And I think that that's a really critical component for this experiment. Very good, team. I think you've got some terrific ideas here.
Yeah, very nice. Very good job.
It's very unique that you're punching holes. That's really cool. And you wrap the wicking. You might want to also try different types of wicking. Not just the cotton. There are other materials that do maybe a little better job. I don't know, try it. But also it's important to remember that the USB connection, which is on the top, is what's going to move your thing to go down once it launches. So you definitely need to link up with that USB connection with your Arduino, your little Arduino there. So it's a lot. Awesome.
Do you plan to have your wicks already wet, or are they going to be dry when they first make contact with the water?
They're going to be dry because they're sitting above the box, and then because it's puncturing into the material, once it punctures into the material, that's when it has access to the water, and it's when it touches the water, it moves the water upwards into the direction of the growth.
Okay.
Right. And part of what I'm asking is how long does it take for that to transmit the water into your soil? It may be longer than the 5 seconds that you have.
Yeah, that's why the food coloring is good, and that's why and you may want to just test it with a camera to see how long it takes.
Yeah, and to make sure your camera picks it up, because the whole value is to see what's happening in microgravity. But you can do microgravity in your room, in your building.
Classroom, yep.
Yeah, just make sure when you drop it, anything in free fall creates microgravity. You don't want to drop it and it breaks. So drop it on a pillow or a bed or something.
Right. Well, and if you get to control when your box cuts into the water, that might be your timing ahead of the drop might also be valuable. So if you find out that it takes 3 seconds for the water to travel up your wick, then make it drop 3 seconds before it does the 0G drop.
Yeah,
all right.
Because we know when that'll occur, and you can always program it. So if you want, you can get the drop and then set your Arduino like 2 seconds after the drop, release that. So that could be programmed. All right, nice work.
Also, look carefully at what your focal length of your camera is. And that might also adjust the thickness of your media that you're testing as well. Team, I think you guys have some terrific ideas.
Yeah,
Excellent.
I like it. Very nice.
Thank you.
Thank you very much, girls.
See you.
Okay. Just let me know, and I will sign them. You could just step off to wherever you normally keep it.
Hey, Glenn, wanted to let you know we have a meeting right now with Mike Schroed.
Oh, do we? Oh, we do? Okay, let's go.
Yeah. Question, is it on Zoom? Is it on Zoom? Yeah. Is it on Zoom or Teams? I don't remember which.
I can't remember.
All
I'll
right.
be right back.
Thank you, guys. It sounds like you guys push off to another meeting, so I'll catch you on your
Thanks
way.
a lot.
Have a great Thanksgiving.
Yeah. You too. Thank you so much. And the kids can always ask questions. Okay, bye-bye, guys.
Bye.
Thank you so much.